Okay, so these first couple of ones, as long as we're comfortable with the notation, we can approach them in a similar way, right? I know I'm choosing from 12 students, and I want to choose 3 of them, so I write that as 12C3. What would that be equal to? What did you guys get for that one? 220, cool. What's this one going to be now? I've got, again, 12 things. So you see in all of these, I've got the same number of things I'm choosing from. What's actually changing? It's how many you're actually choosing. So 12C5, Eva, what'd you get for that one? 792. So quite a lot of different ways you can choose these people, right? Laura, next one?
I got 220.
Oh, 220 as well. What's going on there? Yeah, the same number. Can that be right? And the next one is the same again. Okay, 12C7 is also 792. Is that what you got? Okay, so I just want to show you that we can just calculate these. But there's also an interesting relationship that's happening here too. Matt, you think you know what's going on?
Yeah, like when it hits half, it like starts to go back down.
Oh, okay. I'll come back to that in a moment, but I want to just go back to these specific examples, right? Let's look at these two, 12C3 and 12C9. We got the same answers there. Why might that be? Something you might notice about 3 and 9 is that if you add them together, you get 12, okay? And that's actually true for 5 and 7 as well, right? Why that might be, just think about that from like a scenario perspective, right? If I say I'm choosing a team of 3 students, maybe I'm saying, okay, these are the best sportsmen in the team. I want to choose them to send off to zone or something like that. Think about what choosing 9 students would imply. Choosing 9 students is like saying, hang on, you 9 are the worst in this team, and like I'm not choosing you guys. Does that make sense, right? They're kind of the opposites of each other, but the result is going to be the same, right? If you want to see that from a mathematical perspective, think about what the definition of NCR actually is. NCR was equal to n factorial over r factorial n minus r all factorial, right? So what was 12C3? That would be 12 factorial over what? Yeah? So 12 minus 3, or that's just going to be 9 factorial, right? What would 12C9 look like? Well, I'd still have 12 factorial. What's my r going to be in this case? It's 9 factorial. And then I'm going to have 12 minus 9 all factorial, which ends up being the same thing. Okay, so even though we can use this as a calculation, we can see there's an interesting relationship going on here. If these two numbers add up to give me my n, all right, they're going to give me the same result. And that's something we're going to explore later on, but keep that in the back of your mind, right? Let's look at these ones now. How do we approach these where we have some restrictions? Obviously, this first one we don't have a restriction. So for part A, again, just thinking about how many things you have. So I'm selecting from a group of 10, I'm selecting 4 of them. So that would be 10C4. What does that give you, by the way? What is that in? Punch it in. 210. Okay, again, quite a lot of ways. Now, young people. The youngest must be excluded.
What?
Okay, so it's very unfair to them. Now, they'll always use different kind of words. Maybe this is the youngest, maybe the oldest. It doesn't matter. Either way, one person is excluded from my selection. How can I adjust for that in my calculation? I'm still thinking about a combination. I'm still selecting a group. But how do I account for that? Okay, so instead of selecting from 10 people, right, Laura's saying, hang on, if you just take out one of those people, you're going to have one less people that you can actually choose from. So your n value here is going to change. It's not going to be 10 anymore. It's going to be 9. So that's 9. I still need to choose 4 of them, though. So 9C4. What's that? 126. Awesome. Can we apply the same idea to now the youngest must be included?
You just change the 4 to 3.
Okay. So,
You're picking out of
okay, so I've got this person now. Before they were excluded, but now they're included. I'm saying they must be in that group. Okay. So that changes 2 things. First of all, that changes the number of people that I can choose from, because this guy's already been selected, right? So I only have 9 people I can choose from. But this time, they must be included. So they have to be in the group, right? So the group now actually has 1 less people that I can put in there, right? Because I'm saying they must be in there. So now I'm only choosing 3 of them, okay? 9C3. you want to check that? 84? Is that right? You just zone out.
Yeah, I mean, Harry just, I don't know.
Okay. Probabilities. We love probabilities with perms and cons because we know what probability involves. It involves saying, okay, what's my sample space? How many possible ways can this occur? And what's the number of favorable outcomes? Like, what's the number of ways that I can get the youngest included? And again, we've done both of those parts there. The number of ways that the youngest person must be included is 84. And my total number of possible ways is 210. Can you simplify that for me? I'm not sure if I did that in my head. How much? 2 or 5. I think we saw that fraction before already. That's funny. Any questions about that one? So can you see how combinations are different, right? We're considering now where the order doesn't matter, but we can approach problems in a similar way using this notation. So when we're looking at these combinations, okay, it's really helpful to think about what you're actually being asked to do. If you have n objects and you're choosing R of them, that's essentially at its core what we're looking at, right? So if I'm looking at no restrictions, I know I have 52 cards, and I'm choosing 4 of them, so that's 52C4, which I assume is quite a large number, is that right? What is it? Just out curious. 270,725. So it's 270,725 different ways I can deal out 4 cards to someone, right? Because remember, it doesn't matter what order I give them in, right? It's still one hand at the end of the day. What's the way though? Now I need to select these cards correctly. What's the way though I can only get red cards when I pick this up, right? Because think about what we're actually doing here. What's actually changing? I'm still picking 4 cards, but how many cards can I choose from now? 26, right? Because how many red cards are in the deck? There's 26 of them. So essentially what you're saying is, although, yes, there are actually 52 cards in the deck, right? What you're saying is, how many ways can it happen where I'm really restricted to choosing 26 of them, and I'm still choosing 4 of them, right? That's what this is. It's 26C4.
It's kind of like, that makes it sound like half the deck out, eating
It almost makes it seem like that, right? But all you're saying is, I'm not interested in the scenario anymore. I'm interested in how many ways can I get only red cards. What you're essentially saying is, yeah, I am chucking out half the deck, and I'm only picking from 4 from those 26 there. Yeah? Does that make sense? Right? Because it will give you the same result, even though it seems strange, I'm just like chucking out half the deck. I get what you're saying there, right? What is that? Again, probably a large number. 14,000. 14,000. Okay, cool. Can we apply this idea to diamonds now? Yes. Okay, so we've got this idea. I'm limiting my selection to only diamonds now. There's 13 cards in each suit, so that'd be 13C4. Someone shout it out. 715. Okay, so much less now, right? Here's my question. What's the probability that when I pick 4 of these cards, they will all be the same suit?
13C4 times 4.
Same way they were suits.
Okay, so first of all, what is a suit? You know, hearts, diamonds, clubs, spades, right? But we already found what was the probability of only diamonds. It was 13C4. But hang on, how many suits are there in the deck? There's 4 of them, right? So if you want to think about how many ways can you get it where they're the same suit, you take the result and say, well, because there's 4 suits, we just multiply that by 4, right? So the same suit, the ways we can get the same suit, that's not just 13C4. There's 4 of those suits and 4 of the ways that can occur. So 14 times 13C4. And if I want probability, again, I'm thinking of sample space. So my no restrictions was 52C4. So we can calculate that now. So the probability, same suit, 4 times 13C4, all divided by my sample space, 52C4. Right? Does that make sense? Right?
Maybe. Like, yeah. But I wouldn't have. I didn't even know what a suit was until.
Oh, really?
you said it.
Okay.
Over 4,165.
Yeah, we can still write it. 44 over 4,165. So not too high.
Over 4,165.
Thanks, Matt, even though Laura just said it.